Hello, Neil.
Hey, how you doing?
Yeah. Okay. It's late for you, suppose. Okay. So let me see. Yeah. So okay. The main idea is that so maybe we can say Casimir analog
Okay.
of, let's say, any system,
Yeah.
any fluctuating system
Yeah.
Yeah. By fluctuations, we mean uh, oscillations of all frequencies with equal magnitude.
Right.
Okay. Then the energy associated with that would be equal to, so this will be some constant. Let's say, let me call it, I think we use some beta maybe.
Zeta, right?
Beta probably, beta, alpha, beta.
I think we use Zeta.
Zeta
Yeah, I think
or
so,
nu
right?
maybe, nu. Let me see. I think let me be more careful in this choice. Let's see.
Oh, I think we used Eta.
Yeah, yeah,
The
yeah. Eta. Yeah. Okay, that's better. Yeah.
yeah.
So let's say
Oh,
we.
I'm sorry. I'm sorry. Could you
Mhm.
just give me 1 sec? Something just came up. Sorry.
Okay.
Like 10 seconds, sorry.
Mhm.
Sorry. Yeah, my
Yeah.
bad. Yeah.
Okay. So we are going to say it is energy is eta that depends on the. It is going to be constant for the system. Eta times angular frequency. Okay.
Okay.
Okay, so let's just go by units first. Energy is
Joules?
dimensions are that of joules, right? So joules, let's say, or dimensions of energy.
Yeah.
And this is, of course, 1 over
Hertz.
time, like
Yeah.
frequency. So this is in hertz.
Okay.
And that leaves us with this unit of uh, eta. And it turns out that it will have the units of angular momentum.
Okay.
Angular momentum
What,
has
force times lambda or something?
force times m v distance. No, not
No.
force times distance.
Oh, that's energy. That's energy.
Yeah, force times distance will be energy, correct? That's
Yeah.
right. This will be unit of momentum times distance.
Right.
So basically joules per hertz. That's another way of.
I love how they don't have a unit for, they don't have a name for the momentum unit.
Correct. Momentum unit doesn't have a name,
Yeah.
and angular momentum unit also doesn't have. So technically, this will be meters. Like, so it is meters or kg.
KGM over S, right?
Exactly. Yeah.
Yeah.
So it is kg meters per second. That's linear momentum, and then you multiply with another distance for angular momentum. So it's kg meters square second square.
Yeah.
Okay. So eta is a system dependent constant.
Yeah.
So once you select your system, for example, we are talking about a water tank, then that remains the same. If you were to do this for sound, then that will remain the same. And omega is angular frequency or just frequency.
Right. Yeah.
It's basically frequency, but it's multiplied by 2 pi. Okay.
Okay.
So then, I should also say that there's a small catch here. So I should say so omega is not just frequency, it is omega angular frequency of the nth mode.
Okay. Yeah.
And there are infinite modes. So you have to, or if there are as many modes there are, you have to sum all this to n. Okay.
Is this
And
N, this N is different than eta, right?
yeah, this n is different from eta. Confusing, right? Maybe make it m.
Okay. Yeah.
So make it m so that it's less confusing. Okay. So energy is equal to, rewriting this, since eta is a constant, it comes out, and you just simply have to sum up all angular frequencies.
Okay.
Okay. So frequency is related to wavelength. So it is frequency times wavelength is equal to velocity. Times wavelength is equal,
yeah, that makes sense. Yeah.
to velocity, correct?
Yeah.
And since we are talking about the nth mode or mth mode, we will say this is m, lambda m, and v remains a constant.
Yeah.
Okay, so we will like to do this for lambda m if necessary. Yeah. So that's
So is lambda like the wavelength of an nth mode or mth mode?
mth mode. Yeah, exactly. So this is omega m, and lambda m is wavelength of mth mode.
Okay. Yeah.
Okay. So that's what it is. So now the point is, what are the modes? So the problem boils down to finding all the possible modes, finding the wavelength of that mode, and converting that into frequency, and then adding them all together. Okay.
Yeah.
So let me put that again. So energy is equal to eta times v, again comes out of the summation, and we sum over all possible frequencies, or you can say 1 over the wavelengths, 1 over the wavelength of all the modes. Agreed?
So how'd you take v out of
Because v is the constant, right? For a given system, like for our tank,
Yeah, it's
the
always
shallowness, everything we keep fixed. So
exactly.
it comes out of the summation. It's
And
not,
then
it's not mode dependent.
okay, and so you replace it with 1/.
And then so omega m is V over lambda
I
m
understand. Okay, yeah,
comes out, and okay.
yeah.
So what are the modes? So for finding the modes, now there are two situations we will consider. And let's see, first is, so case one. Case one is when you have the modes, we are calculating the modes where on both ends of a linear system, the
Yeah.
oscillations stay stationary.
All right.
Okay. And then we ask, what are the wavelengths possible? So let's say this is length L. This is your length L of your tank, for example. Okay. And what are the oscillations possible? This, of course, zero oscillation is a solution. Then the simplest is when you have a wavelength of this kind. So that's half the wavelength, right?
Yeah.
So lambda 1 will be equal. So the first mode is, so lambda is, L is lambda over 2. So this is 2 times L.
Yeah. Okay.
Do the second situation, we have this, and this is lambda 2 is equal to L.
Yeah. So this is M1 and M2, right?
Yeah, so
Yeah.
yeah, or M is, so here this is M is equal to 1.
Yeah.
Now it's M is equal to, so first mode, second mode,
Second.
and M equal to 3.
Is it mode or node?
It is mode actually. It is
Mode.
in which mode is it oscillating. The node is when the points where it does not oscillate, those are called nodes. So node
Okay.
is different.
All right.
Okay. So here this will
When I
be,
did sorry, when I did the black body derivation, they were talking about nodes. So
no, it will be mode actually.
really?
Yeah, I'm pretty
Yeah,
sure
okay.
it's mode.
He was
the
talking
same,
about
it's the same
yeah.
idea. It's the same idea.
Okay.
Same idea. Yeah. So this will be 3 by 2 lambda is, so it is 2 by 3. So lambda 3 is equal to 2 by 3 L, and this is 2 by 2, and so on.
This is gonna sound stupid. Is there a reason for the M equals 2 that you dotted the top part and
Oh, no.
okay, all right.
It was just,
I'm just making sure that wasn't
yeah.
some trick
No,
that
no,
was
no.
yeah.
No.
No, it doesn't matter, yeah. No.
Yeah, good point.
Okay.
Yeah.
All right.
So, and this is one, and the pattern is reasonably clear.
Yeah.
So mth mode will be, so lambda m will
Right.
be 2L over m.
Right. Yeah.
Okay. So what will be the energy then? So energy would be equal to eta V. Now I had to add this all up, but remember I am adding the inverse of this, right?
Correct.
So I have to do 1 over 2. So I divide by 2L. I divide by 2L, and everything up adds up. So it is 1 plus 2 plus 3 plus so on.
And that's negative 112.
That's negative 112. Okay. So that's
Isn't that like assuming that Euler's theorem is correct or something? Or
no, this is pretty much universal. It is called
Ramanujan's
from the Riemann summation formula.
Riemann summation. Yeah, that's what I meant. Yeah.
Formula. Okay, and
Like,
that is something that you will have to motivate, but I would say that is sufficient stuff on that.
I think there was a thing with Riemann summation is that you can pretty much, if you take any number like above 3, you can make that set of numbers equal to that. right? Or
I don't know.
because like I saw this proof and it was that you take a certain number of numbers, so like 1/1 plus 1/2 plus 1/, or whatever it was, like all the positives, and you can add it up, and then as soon as you go over, you
Mhm,
take negatives, and as soon as you go under, you take positives, and then you go negatives, and you just can go on forever with that,
mhm, mhm.
supposedly. Or
Probably, yeah. I'm not completely seeing it, but uh,
I don't know exactly. I mean, I can't. It doesn't matter, I guess.
yeah. So yeah, let's proceed so that
Yeah,
okay.
it's yeah.
So this is now we have, and is it necessary? Should I call this L or A is good? Yeah, let's call this A just so that
Oh, is that what you were calling A in the lecture? I know it was a while ago, but
probably you mean in the lecture means in the notes with.
yeah, like the lecture you shared with me, you replaced lambda
Yeah,
with A.
probably because I mean, that is the only reason why I'm changing. That is nothing, no big deal. It's just that usually in the notes that we have in writing, me and Prakash, like we always say it's A. So
Okay,
it matches with
right.
the
Yeah.
notation that we have. But you can call whatever we want
Yeah,
and
yeah, that's
that's
fine. Yeah.
perfectly well, right? So this is A. Yes, we must have used that. So it is -1/12, and immediately we have eta times V over 24A.
Yep.
Okay.
Okay. Yeah.
Now that's the energy. Force is equal to the negative, it's always the derivative of energy with respect to the distance, right? So it's A. So for what distance or energy tries to be minimum, that's another way of saying it. So since energy tries to be minimum, so force is a manifestation of the fact that energy tries, and the negative sign is the point that it tries to be minimum and not a maximum. So you simply take a derivative in here. So negative and a negative makes it a positive, but then you take the derivative, which again makes it negative. So that's
So you're taking the derivative of E with respect to length, or
yes, length is A. So we are saying that if you were to, in an abstract sense, imagine that A was larger or smaller, what
okay.
happens to the energy? So you have this tank,
Yeah.
and if the tank were to have a slightly smaller length or a larger length,
Yeah.
then what will happen to the energy? If the energy tries to be minimum when you stretch the tank,
Right.
then the pressure will be to stretch the tank. It will try to push the tank out. If the energy is less when you decrease the length of the tank, system will tries to attract it so that the length is smaller, and that shows up as a force.
Right.
Does that make sense?
Okay. Okay.
So this is pretty much, if you were to take the derivative, it's a square, right? So it is eta
Yeah.
v over 24 a square.
Is it not positive, or
It is
oh
negative because negative of a negative, and then the derivative also has a negative. So there are three
okay, yeah,
negatives
no,
here.
I forgot you put a negative in the front. Yeah. Okay.
Okay. So that's your formula for the force. This is the classic case of Casimir, but that is the case too, right?
But so for this, would I just plug in my velocity and A, I guess?
Yeah, velocity and A, and eta, remember, is a constant. So you cannot find that out. That
Right.
depends on the whole system,
Okay.
right? So you will only have to show that, okay, I mean, if you have to really have the expression for this, you will have to change the length of the tank somehow and
Yeah.
show that it is the force is 1/a square. But remember, you're not really measuring forces.
Okay.
You're only going to show that this is attractive, correct? You're
Oh, I understand. So you're saying, okay, I was confused. So if you take the derivative, you're essentially multiplying it by m, which takes you from joules to newtons.
correct, exactly.
Okay.
Yes.
Yeah, I don't know why I didn't pick up on that, but okay.
Okay. Good. Okay.
Yeah.
Reasonable. So force, there is a force which has a certain direction now, like energy tries to be minimum. or smaller a.
But why do we make the derivative and the answer? Why can't we have both of them positive? Or
Maybe if I'm understanding your question correct. So if you have energy, if I were to plot this energy,
I'm just talking about the derivative. That like why did we make the derivative of energy respect to length? Why did we make them both negative? Or
both negative means
like couldn't it be? I mean, I don't know. Would it be of energy respect to length equals positive?
force.
There's a
No, the system tries to minimize the energy. That's the governing principle.
okay.
And since it tries to minimize it, that's the interpretation of that negative sign. If
Okay.
you were in a universe where the energy tries to be maximum,
All
then
right.
you will have positive.
Okay.
Did I clarify?
So it minimizes energy, you're saying.
Yes. Mm-hmm.
Like can you explain like I guess like
Yeah,
how?
for example, let us say like we always say that if I drop a ball, correct,
Right. Yeah.
from a height edge and it falls down,
Yeah.
you say that, oh, that is gravity pulling it down, like earth is trying to pull it down.
Right. Yeah.
That's one interpretation. But
Okay.
a more fundamental interpretation is that let's calculate the energy of the ball when it is at height 1 meter, and let's calculate the energy of the ball when it is at height 0 meters. Whichever is lower in energy,
Yeah.
the system will go to that spot, or will
Right.
try to go to that spot. If it has the freedom to move, it will move to that spot.
Okay.
Okay. So
Yeah.
gravitation, if you calculate the gravitational potential energy, it will be higher at 1 meter and lower at 0 meter. But we are working with negative numbers. Remember, if I
So this is
decrease my
about
energy,
potential energy?
this is potential energy, exactly.
Okay. All right.
So this is the energy associated with 0 point energy. If I were to plot energy as a function of A, this will look 1 over A square, right? Since it is negative, it looks like this.
Right.
Oops,
Yeah.
sorry. Right, it looks like this, which means that as I decrease my energy, so this is 1 meter,
Yeah.
and this is 0.5 meters. So the energy here is somewhere here. And as I decrease my A, my energy decreases.
Yeah. Okay.
So the system will try to decrease the distance.
All right.
Which means that if you have a water tank of length A equal to 0.5 meters,
Yeah.
preferably if it had a choice to shrink, it will shrink to 0.5 meters and in fact shrink to 0.
Right.
Which means there is an attractive force. It may not have the ability to do that, so it shows up as a force.
So you're saying that because of the way the graph is, A would rather, if A had to go in a direction, it would rather be less, which means
Energy is less.
so the length would
Contract. The tank would contract if it had the ability to do that. For example, if you take our universe, right?
yeah.
Our universe, does it contract or expand?
Expand.
And if it is expanding, that means there is the energy of the universe is lower when it is in an expanded form. So it is trying to expand, or it is expanding.
So it can lose energy?
In principle, it can, but universe is probably not a very good example in the sense that you cannot lose energy to the system outside, right? But if you're in the universe, then you can transfer energy from one system to the other. The universe probably is not the best example because it's not a it's a closed system.
So what you're basically saying is that the system wants to lose potential energy.
Correct.
And so in order for that to do that, A would have to be smaller, which means that the length is getting smaller and it's pushing a force on the inside.
Correct. Exactly.
Okay. All right. That makes sense. Yeah.
Exactly. Good. Okay.
All right.
That is case 1. But
Okay.
there is a case 2, right?
Yeah.
And that's the what we call the hydrophobic equation. So this is case 2 now.
And is this hydrophobic versus hydrophobic or?
The first one was both hydrophilic. So let me call this philic, right?
Oh, this is philic.
Yes. Like both are 0, right? Both places are 0. So it doesn't,
Okay.
so the water is not liking to move away from the surface.
Oh,
I don't know the spelling of philic, probably it's correct. Yeah. Okay.
that's probably it. Yeah.
And case 2 is philic phobic, right? One side is philic
Yeah.
and the other side is phobic.
So is there like a, so the philic shouldn't come together, should it? Or
Philic will come together because in your case you will be having 2 identical. In fact, phobic will also come together.
so would, because when I was first running the experiment, I wasn't putting the hydrophilic tape on it at first. I've been keeping it coatless. So like I guess
Whatever it is, as far as they're identical plates, they will
yeah.
always be attracted.
Okay, so I can show all 4 different cases basically.
Yes, exactly.
All right, but we don't really need a derivation for the case where neither of them are philic or phobic.
You mean, but then either it is philic or phobic, right? What do you mean? I mean, that is, you mean it's 0, like, but then what is the boundary condition here? It has to be either stationary or moving. Somewhere in between will be a linear combination of that.
Okay.
Yeah, in principle, yes, I would say, yeah, your question is correct. But we are going to consider only simple situations. How about that?
Yeah. All right.
Okay. Like big, it can be done, but it is more work. Put it like that.
Right. Yeah.
Okay. Okay. So case 2 is philic phobic. So what we're saying is you keep this fixed, and this is so let me show that as a dotted line. That means that it has maximum value there, right? And then we see that m equal to 1 mode will be when this is fixed and that is maximum. So it is kind of a quarter wavelength is what length is. Right?
So the left is philic and the right is phobic.
Exactly.
Okay. All right.
So lambda 1. So it is 1/4 of lambda 1 is equal to L, right? So it is 4 times A, I suppose.
Okay. And it's 4 times A because it's 1/4 of a normal period.
Yes, exactly.
Okay. All right.
Okay.
Yeah.
And m equal to 2 currently is. So you would go like this, right?
Yeah.
So it is 3/4 of wavelength is A. So this is lambda 2 is 4A over 3.
Right. Yeah.
It's 4A over 1. And we can show that lambda m will be equal to 4A over 2m plus 1.
Oh wait, why was you made the second one 3?
Because there are 3, so 3/4 of wavelength is equal
Oh, I
to
understand.
A, right?
Okay.
So,
All right. Yeah.
okay. So we have the formula for lambda m, so we can calculate the energy again. So energy would be equal to eta v over 4A this time.
Yeah.
And now we are not summing over So again, all the modes, but now it is not all the integers. It is 1 plus 3 plus 5 plus so on.
Okay.
And that's equal to, so to do the summation, there is this like very simplistic trick.
Could you subtract by 1 and divide by 2?
Subtract by 1 or add up all the even numbers and then subtract all the even numbers. Probably that's what you meant.
I was just going to say subtract the whole sequence by 1 and then divide it by 2.
Subtract the whole sequence.
Because then you get 0 plus 2 plus 4, and then you divide it by 2 and you get 1 plus 2 plus 3.
But then why should it be the same? Like you are subtracting by 1. Oh, in each term, you mean?
Yeah.
Oh, so it is 0 plus 2.
Oh, you can't subtract by each term. No, you can't do that.
Yeah,
Yeah,
if you do that, but then you have to add
yeah,
up
no,
all of
yeah,
them.
yeah,
So
no,
it's
you
not
can't do.
clear.
My bad. Yeah, okay.
Okay.
I'm confusing myself. All right.
But pretty much the same. Like idea is very similar. So you do this 1 plus 2 plus 3 plus so on. So you fill in the sequence and subtract out the ones that you
Oh, I
filled in.
understand. Okay, yeah, that makes sense.
4
Minus 2 times 1 plus. Okay.
Exactly. Okay.
So.
And this
So
one.
1/12 would be the total.
Exactly, but it is positive this time, correct?
Yeah, positive 1/12. Yes.
Exactly. So that's the only main piece there, that it changes sign. Right? If it changes sign, the force now.
Is it not 48?
It's not, right? Because this was minus 1 by 12. Right? Minus of 2 times minus 1 over 12. Right? So it is plus 1 over 12.
Right.
Is that right?
Yeah.
So that, and 12 times, oh yeah, you're saying, oh, I see what you're saying. Is it? Help me. I guess it is, right?
Yeah.
Because 1 plus 3 plus, did I miss anything? So length was 4a, correct? So you're saying, yeah, so it is 48, yeah. No, you're correct, yeah.
No,
Check on it.
the last one was 24, I think. Negative.
Last one means
The case 1.
case 1. Yeah. That we did get 24, right?
Yeah.
Yes. So I think, yeah, so it is 48. Yeah. I don't remember. Yeah. Okay. 48. Good. Okay. It doesn't think so. Yeah. I think, yeah, minus, yeah, right, everything else remains the same. Good.
Oh,
And
so
if
is sorry, go ahead.
and just for to complete it, so this is now a positive number, right?
Yeah.
So this is eta v times 48a squared. The moment force is positive or energy is positive, that means to say that now if you were to plot energy versus A,
Right.
it is positive, so it looks like this. So as you change your A, energy is actually decreasing again, but now it tries to increase A, so it tries to expand the tank, which means it's repulsive.
Oh, so as A decreases, energy increases.
Exactly, right.
And that would try to expand the tank. Okay. And so this wouldn't have like the force between the plates?
Yeah, so I mean, oh, maybe I am telling this as a tank, but our tank is the area between the plates. Like think of this as a space in between the plates. That's our A.
Yeah.
right? So when I say that expand the tank, so the plates will try to move,
Okay, I understand.
right? So our region is in between.
Right, that's right. The region is the
Yeah.
of course.
Like that's a region we are talking about.
Okay.
Okay.
And you said because we have, so like why is the system trying to lose potential energy, I guess?
That's okay. That is a postulate, if you want. That is a law. That is the governing principle of almost everything that you see. It's not almost. If you want to take one information that can explain almost everything in chemistry, biology, science,
Yeah.
anything, is that energy of the system always try to decrease. That's
Okay.
it. That's our governing principle. You can say it is the Newton's law. You can say it is thermodynamics, whatever it is. That's the governing principle of nature.
Okay.
That energy tries to be minimum.
And so like what does this energy would change into? Oh wait, no, it doesn't change.
That's a force.
Okay.
If the system has the ability to change, right, that is what it, if it has the ability to move, then it will attract.
Okay.
So it is changing its A so that energy is minimum, which we say it's the force. That's an interpretation that, oh, this is the force.
Okay. All right.
Right?
I think I understand it. But
Mhm.
so this apparently relates with the Casimir effect.
Yeah. So now the whole point, what is the whole point here is that the first point we are saying is that the sum of all the modes is equal to the energy. That's the idea of Casimir energy. So notice there is nothing in, even though we are actually supplying the modes,
Yeah.
in Casimir effect, the idea is that there is no one, like if it's our universe, no one is providing that oscillations. It's just fluctuations.
Okay. Yeah.
Just because your ship is in the ocean and there are air fluctuations in the air, there is an oscillation,
Okay.
and that will cause two ships to attract.
Okay. And then we are going as further to say that so the only similarity is that you're summing up all frequencies of these oscillations,
Correct.
and that we're going to say is that this is using water waves to
Exactly. So
Okay.
our system is entirely different. In Casimir effect, you say the whole space, like if you remove everything from space,
Yeah.
the vacuum itself, there are fluctuations in the energy there.
Right. Yes.
And that's what we're talking about. So that's called the 0 point energy.
Okay.
Now you say that if you have water, ocean is very steady, perfectly steady, but then there are oscillations in that just because things are not perfect.
So would you say it would be a okay, so I was making the slideshow, like working on it, and I created a slide because I know I mean the main part that shows the result is using Ramanujan summation. So if you think I have space, should I like include the slide I made?
Yeah, sure. I would say include all that. Yeah.
Okay.
I mean, it's just that, see, the only challenge with that is that people will not understand that very well.
I
You
actually
know?
made a really I can show you. It's pretty
Yeah,
simple.
go ahead. Show me, yeah.
I mean, it's pretty simple. Like I found it on the internet. I was looking for a couple ones. This was the simplest one I could find.
Mhm.
But you have
Yeah.
3 series here,
Yeah.
and it's just a 3-step. I mean, it's a lot of numbers and a little bit of space, but at the same
Yeah.
time, it's just add and subtract and 7th grade algebra. So
Okay. So good. But this is exactly the way it is proved. Now,
okay,
the point is, this is very, I mean, you will not believe it yourself, right? I mean, oh, is this really what it is? We are subtracting infinities. But the idea is that you can do this in a sophisticated way, but the result remains the same.
yeah.
Okay, you can make this better and better, but the result is going to not change.
Right.
So when, I mean, it depends on whom you're talking to. If you talk to someone, if you present this to a student, then they might not be aware of this, and then that is a,
Yeah.
you lose the audience in a sense.
Okay. I think that answers everything I was looking for, honestly. That's really good. Yeah.
Okay, good. Yeah, yeah.
Um,
I'll send you the video also so that,
yeah, I mean, I took notes, but like, yeah,
okay.
I guess it would help. Like, sure.
Yeah, I'll send you the video so that if you want, you can think on it or refer at least, yeah, if necessary.
In the slideshow, how do you want me to credit you? I guess.
Oh, I would say very, very vaguely, very superficially, just say uh, for for consultation or very some. I mean, I hardly did anything, right? Or
I mean, you
motivating,
helped me a
maybe
lot with.
just
I mean, you
motivating.
kind of showed me the theory, so.
Yeah. So in that sense, you can say that in yeah, this was suggested or motivated by Prachi and me. That's it. This is
So
reasonably standard stuff. So I mean,
so
I'm
I'm thinking
thankful.
at the last slide, there's a bibliography at the bottom, all like right, saying motivated by. Um,
Acknowledgements, maybe. I mean, typically the standard is acknowledgements. So we thank this and this person for what's the right word? I mean, guidance. If you feel
Guidance is
comfortable about
probably.
that,
I'd say
guidance. Yeah,
guidance is a good word. Yeah.
that's it. That's sufficient. Yeah,
All right.
yeah.
Perfect.
That's good enough. And even if you don't do anything, that's also fine. That's perfectly okay.
All
But
right.
I think that's appropriate, I would say, because anyone would ask, how do you know this stuff? So if you have a guide, if you put our name in it, then no one is going to doubt that, oh, okay, how come you know so much?
I always hate the question they ask. They always ask, "Why did you do this project?" And like, I mean, I feel like it's not a bad question, but it's just like it doesn't contribute to the
Agreed.
purpose of the fair, I guess. But
Very,
because like
very
I think
reasonable.
that I gave that whole presentation last year, and the only question they asked me of everything that happened in the presentation was, "Why did you do this?" And I said there was a problem, and I tried to find a solution because I couldn't think of anything else to say, and I really was just I couldn't understand why they couldn't ask something about the presentation. I mean, it's a question, it's askable.
Like maybe what you can say is, suppose it comes back again. Like, I mean, what you could say is that I have friends or family who works on Casimir effect,
Right.
and they recently in their calculation came across this idea that or it's reasonably well known, and but they came across this idea that electric and magnetic effects, there is a repulsion, which is known in
Yeah.
Casimir effect.
Right.
And we were also aware of the fact that there is a Casimir analog of in water waves.
Yeah.
So if there is a Casimir analog of attraction, would there be one for repulsion?
Right.
And we thought hydrophobic might be a point to
So
consider.
were your works with including the water wave analog, or
Your what?
did your like what you did with Banca and Prachimosi, did that include water waves? Or
No, 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 not at all. Not at all. We are not even, actually, that problem never, like we worked on a lot, but then we got some other results in it. But our goal was to get a, like we have this, what is called delta function plates, and introduce them in between, and it will not be seeing through it. But that did not really work. So
yeah.
I would say we did not get a result. But in while doing it, we got something more interesting. Or Venkat got something more interesting. So he's writing it up, and hopefully in the next 2 weeks or so, he will be communicating that. So it is
Um
mostly his work. I think we are planning, it will be told as his work. So it is nothing to do with repulsion at all at this point. The problem completely changed during the process.
I think should I email if all goes well, should I email Professor DiNardo maybe? I was thinking of
Emailing him for what?
I would just let him know because I mean he seemed to be pretty interested in the.
Yeah, I would say if you, yeah, I mean, it's sure. I mean, whatever you do, update him. That's just politeness, I suppose, because you wrote a email to him and he helped you pretty much. He was reasonably prompt. So I
I
say
didn't
that,
really. I mean, I don't know if I received. It was interesting. I mean, he definitely answered something, but
yeah,
yeah,
yeah, yeah. I mean, typically, I mean, even just responding is good, right?
yeah,
I mean, at
yeah,
least, yeah, he got that point. So I would say if you feel comfortable and you're interested in communicating with him, sure,
yeah,
like updating, this is what I did and this is what I plan to do. If you don't do it, that's also perfectly
yeah,
fine.
yeah,
I mean, there is nothing wrong in it. It's surely, I think the only thing people worry about these things is that, okay, you're proposing something slightly interesting. If there is really repulsion, then you have
right.
to make sure that, yeah, I mean, before you write it up, someone else doesn't come up with it. But I don't think we have to worry about it. There is no competition here as such.
Yeah, I don't think
So
so. I mean,
feel free to
I'm a high
discuss.
school student. I don't think there's.
Yeah, yeah. So feel
I
free
mean,
to,
if he was willing to help me that much and like
yeah.
write like a full out email, I doubt he'd be the like yeah
Yeah, yeah, exactly. And I don't think we should, that's the only, like, in the very cutthroat field where there is a lot of
yeah
competition, then people do talk about that. But I don't think in our theoretical physics area there is any such competition. There are enough problems uh, to
yeah.
work on, so there is not significant uh, dearth of these results. And
I was like searching for it because I read a book on it when I was really young, and I can't remember. There was, I wonder if you remember, there, I can't exactly what it was, but there was this problem that was like, a bunch of people were trying to figure it out, and it was, like somebody figured it out, and I can't remember the name of it. It had something to do with like a Pythagorean triple, and that there was only one with like x cubed plus y cubed or something.
Mhm.
Was that, are you
Fermat's
familiar?
theorem?
Huh?
I think it's called Fermat's theorem, probably.
Fermat's? I don't know. I read something about it so long ago and I just completely forgot the name of it.
I think it's Fermat's theorem, and maybe if you're telling this, if we are thinking the same. And in 80s, there was this claim that, oh, I did it. And then it took
Yes.
forever to confirm that that was actually a solution.
And n is greater than or equal to 3. There's no solutions.
Exactly.
Yeah. No, I was looking for that. I couldn't find it. I don't know why I couldn't find it, but yeah.
Okay.
No. Yeah. All right, great. Thank you. Yeah.
Okay. Yeah. Good luck. And
I'll keep you updated. Yeah.
yeah, yeah, yeah. Especially, I mean, even any force, if you see this thing, yeah, take a
Yeah, I mean
video or something, and I'm pretty sure all of
it's
us will be
yeah,
interested.
it's definitely there's slight waves with all the air that's stopping it. And so,
Okay,
but
nice, nice. Yeah. Okay, good.
yeah,
Yeah,
thanks for meeting. Yeah.
yeah, yeah. Enjoy, and yeah, enjoy the work. Yeah.
Yeah. Have a good day. Yeah.
Okay.
Or night, whatever it is right now.
Bye. Yes.
Yeah. Bye.